Hey everyone, great to see you here for our final final demo. These are the key topics we will go through in today's presentation. We are excited to present the current progress of our team project, TechScrum, a project management platform designed for agile software team. It helps teams stay organized by allowing them to create and design tasks, plan sprints, and track progress collaboratively, similar to Jira, but building using our own full-stack solution. Unlike building the product from scratch, we started with an existing code base. So our work focused on two key directions. First, maintaining and improving existing features like ticket and sprint management. And second, developing new features that improve in usability, scalability, and team workflow. We are a team of full-stack developers working together with support and guidance for our supervisor, Kitman. Our team includes Lin, Joe, and myself, Oasis. Everyone in the team contributed across both front-end and back-end for implementing new features to fixing bugs and optimizing existing logic. Tech-wise, our front-end is building with React.js. For styling, we use a mix of style components and SCSS module to build a clear and reusable UI. The backend runs on Node.js and Express.js, and we use MongoDB as our database. Our APIs follow the RESTful architecture, and the entire system is containerized with Docker and deployed on AWS for scalability and consistency. In the final months, our main focus was to introduce several new features to make TechScrum more reliable and user-friendly. These include a visual dashboard, a CSV import-export function, and a global error handling. We will walk through each of those features in more detail shortly. Before that, we had already delivered a range of core features, including ticket management, sprint planning, the board view, and the permission controller. We also delivered a complete Epic system from front-end to back-end, integrated Stripe to support user payments, and completely rewriting the ticket detail card, adding a rich text editor and a structured activity log for better collaboration. Along the way, we also refactored outdated code and improved the backend system consistency across multiple modules to make the system more stable and maintainable. Now let's dive into the dashboard. Its main goal is to help team monitor ticket progressing in real time and see any sprint delay coming ahead of time, so we can catch delay before they happen, and also line the groundwork for future forecasting. We use a rich charts to build 3 clear interactive charts from the dashboard for the dashboard. First, the status overview, a pie chart that shows how tickets are distributed across in status, like to do, in progress, and done. Second, the types of work chart, a horizontal bar graph breaking down tickets type like story, bug, task, and tech debt. Each type has a unicorn icon and color for clarity. And third, epic progress, a bar chart that shows how many tickets in each epic are in each status, making it easier to track large features group. To make the visual more consistency and easier to maintain, we implemented a controllerized color and icon mapping library, so that each type and status always using the same color and icon throughout the platform. Also, all of our charts were built with a responsive design in mind, so they automatically adjust the layout and size based on screen wide, making them more user-friendly across different devices. On the backend, we built 2 new APIs using MongoDB aggregation pipeline to summarize the structure tickets data. When API summarizes tickets counts by status or type within the current sprint, the other one shows tickets distribution by status under each epic. This API ensures accurate real-time data for the front end, making a dashboard both responsive and reliable for team. Now let's hand over the time to Lin.
Let me now walk you through the CSV functionality we implemented, originally inspired by a real need during deployment, migrating existing Jira projects into our own platform. We wanted users to be able to export a project from Jira as a CSV file and then import it into our system. At the same time, we also built CSV export on our side, so users can download structured project data when needed. So in our first version, we built a pretty straightforward RESTful API on the left-hand side, and the user could upload CSV file, and the user would handle everything right away, reading files, parsing that data, transforming it, and then inserting everything into the database in one go. We used the Muteler for file uploads and had logic to treat small files and large files differently. Small ones stay in memory, large ones went to disk. That worked initially, but larger files quickly become an issue. High memory usage, blocked requests, and no feedback if the files was malformed. To solve this, we simplify the flow. Now all the files are saved to disk, regardless the size, and also avoiding memory overhead. More importantly, we moved import logic to an asynchronous model using RabbitMQ and a dedicated macro service. Here's how it works. We will still receive CSV uploads through our main Impress server. Then we use Muteler middleware to store the file on the disk. Once saved, we send the message to a RabbitMQ task queue, passing the file path and metadata. A dedicated import macro service running on a separate repo acts as a RabbitMQ consumer. It picked up the task and performed the full CSV processing and database insertion. In short, the Impress server acts as a producer and the import service is a consumer. RabbitMQ worked as a message broker, functioning as a middle station to route task message to the right workers. Next page, please. Now let me highlight the advantage of this mechanism. First, it offloads the heavy CSV processing from the main application, which improves performance and responsiveness, especially when handling thousands of rows. Second, the setup enables us to process the data synchronously, meaning the user doesn't have to wait for the full import to complete. They can upload the file and continue working while the task running in the backend. Third, it introduces better modularity and fault isolation. If the import service crashed or fails, it won't affect the main server or other user-facing features. Finally, this design also makes it easier to scale. In the future, we are spinning up multiple import workers to handle larger workflows without changing the main system. So overall, we achieved a cleaner separation of responsiveness, improved scalability, and laid the foundation for more reliable data digestion pipeline. We also plan to add some import status tracking and error logging per row so that user can understand what succeeded and what failed. Although this module haven't been totally deployed yet, the entire system is working in development, and it's a strong step towards making our platform Jira compatible. Next, I will pass to Jill.
Okay. We run into a few challenges while building our microservice. Our project is a multi-tenant system. So when users send requests, we first check their subscription plan. If the user is a VIP, they will have their own database. To avoid creating and closing database connection all the time, we maintain a connection pool in the main application. The appropriate connection could be selected from the pool and pass it to the subsequent business logic for operation. However, when using microservice, we cannot directly pass database connections through the message queue. This creates a challenge for connection management. To address this challenge, our initial idea was to move the connection pool logic into a separate NPM package that each microservice could install. With this setup, the main application would just pass a tenant ID, and each microservice would manage its own connection pool using the shared package. However, this approach made the microservice too heavy and add more performance overhead than we want. After analyzing our real-world usage scenario, especially the likelihood of single tenant frequently triggering import-export operation within a short time, we decided not to maintain a connection pool within each microservice. Instead, when a microservice received a tenant ID from the message queue, it established a new database connection and closed the connection after use. Right now, we are managing our microservice using a polyrepo setup. The main reason is that we already have a pretty large code base. Monorepo means a lot of restructuring, change project layout and dependencies, which could affect the stability of our program. So we choose to use polyrepo. That said, monorepo definitely has its benefit. It is easier to keep all the microservice and shared code in one place. That makes updating dependencies and reuse code between services much easier. It also helps avoid problems with different versions and reduce the duplicate work. We will consider switch to a monorepo in the future. For error handling, we have done three main things. Firstly, we standardized the backend error handling by 8 global error catching at the root level, and defining a centralized error handler. With this setup, when writing business logic, we do not need to use try-catch block everywhere. Simply throw an error is enough, and it will be cached and passed to the error handler for the unified processing. Second, we used Morgan to customize our logger and include the error stack in the logs. Then whenever error occurs, we can quickly point out the issue by checking the log files. Additionally, we integrate Logly to manage our files. This allows us to view logs on the Logly dashboard without need to log into the server, which makes the troubleshooting much more convenient. To sum up, in the past few months, we have made solid progress by refactoring our code base for better quality, build new features to meet business needs, and optimizing our system performance both on the backend and front end. These improvements have not only enhanced our product, but also laid a stronger foundation for the future development. Thank you.